Everyday items that utilize springs are ballpoint pens, car shocks, and wire-bound notebooks. There are many others that you can think of around your house. A spring has an original length when no force is applied to it. The extension of a spring is how much longer the spring becomes when a force is applied to it. The elastic limit of a spring is the point to which the spring will resume its original size and shape when the stretching force is removed. Hooke's law states, provided that the stretching force does not extend a spring beyond its elastic limit, the extension of the spring is directly proportional to the stretching force. This is illustrated here, where the blue region, which is a straight line starting from the origin with a positive gradient, shows direct proportionality. In green, where the graph starts to bend and curve, that shows that it no longer obeys Hooke's law. That is known as the plastic region. And finally, at the X, that is where the spring would break or fracture. As we see here, if you have twice the weight, then you have twice the extension. Let's do an example. Without any weight on it, a spring has a length of 5 centimeters. When a weight of 1 Newton is hung from it, the length of the spring becomes 6.2 centimeters. A. What will be the length of the spring when a weight of 2 Newtons is hung from it? And B. What weight was hung from the spring when its length became 9.2 centimeters? So we begin our solution by writing our formula and identifying our givens. When the force is 1 Newton, the extension is 1.2 centimeters, which is the final length minus the original length. We rearrange to make K the subject of the formula. So the spring constant K will be the force divided by the extension, and that gives you 0.83 newtons per centimeter. When the force is 2 newtons and the spring constant is 0.83 newtons per centimeter, the extension will be 2 newtons divided by 0.83 newtons per centimeter. And that gives you approximately 2.41 centimeters to 2 decimal places. The length of the spring will then therefore be the original length plus the extension. So 5 plus 2.41 gives us a total length of 7.41 centimeters. Part B. The extension in this case is 9.2 minus 5.0, which is 4.2 centimeters. The spring constant is the same, 0.83 newtons per centimeter. So the force used would be the spring constant K times the extension E. When we multiply 0.83 times 4.2, that gives us 3.49 newtons to 2 decimal places. An alternate solution, if we use ratio and proportion, since there is a direct proportionality. Using the same givens as before, we now set up a ratio where 1 Newton corresponds to an extension of 1.2 centimeters. So we are to find what extension corresponds to 2 Newtons. If we cross multiply and divide, the unknown extension will be 2 times 1.2 divided by 1, which gives us an exact value of 2.4 centimeters. Therefore, the length of the spring will be the original length plus the extension, so we get exactly 7.4 centimeters. Part B. Similarly, with the same givens as before, we set up our ratio. 1 Newton corresponds to 1.2 centimeters. So what force corresponds to 4.2 centimeters? We cross multiply and divide. 1 times 4.2 divided by 1.2 gives us exactly 3.5 newtons. The advantage of using proportions is that you get exact values, whereas using the formula, sometimes it is possible that you get rounded off values. In summary, the extension of a spring is directly proportional to the force applied, provided that it has not been stretched past its elastic limits.